some excellent work being done at our own university. I'm happy to introduce Alan McCree, who's at the COE. Alan comes to us from, I guess, Georgia Tech by way of Lincoln Labs. Was there a BN in between? Or?
Texas A&M.
Texas A&M. There you go.
There's a little Bell Labs and a TI.
Yes. And so anybody who does anything in speaker ID, language ID knows who Alan is. Most recently, he's been passionate about rigorous probabilistic ways of doing speaker ID, and he'll tell us about it. Will you talk about PLDA?
Yes, I will.
Okay, yes, so you'll hear it, and you'll also hear a scolding saying, "You guys don't be shoddy about it. Do your math properly. This is how it's done." So Alan will give you that. So pay attention.
Yeah, I'm not sure if I agree with that last part, but thank you very much, Sanjeev. I actually kind of wrestled, and thank you guys for inviting me, whoever actually did. I kind of wrestled with what I wanted to talk about. I know, like, Hinek gave a great sort of my life as a speech researcher talk, and I thought about that, and I think I think I have actually some good stories from my speech coding days, but I think not enough to make a whole talk, so I skipped that. So it's going to end up kind of a combination of our latest research, as Sanjeev was talking about, and then sort of some opinions, because I think opinions are sometimes more interesting than facts. And Aaron and Daniel have already noticed there are quite a few opinions in this talk. I think that'll kind of help. And kind of a subtext to that is why you might think that I-vectors and PLDA is a pretty straightforward thing, and can you just give me a reference so I can build one? I think it's actually more complicated than that. And I have to acknowledge, if you don't know this pretty picture on the slide here, that is Daniel Garcia Romero. We had the privilege of starting at the COE on the same day, which was also the first day of Scale last year. And this might also explain to you guys why you always see us talking in the halls for hours and putting formulas on the board, even though it seems like we're doing something that ought to be pretty simple. So just a couple of sort of philosophy points before I get started is in our field especially, you'll see there's a pretty big dichotomy between the probability kind of people, and I use the word pragmatic, maybe machine learning. I'm not sure what you guys would call the other side. Daniel is a full-fledged Bayesian. I'm kind of really more of a signal processing guy when it comes to probability, but I do like the concepts of probability. And the one thing I would say is, regardless of whether you actually use it to provide your best possible algorithm, I think you should always think about your problem in terms of probability theory. Think about what that tells you, what priors, what tasks are, and how you're going to use the outputs of your system to do something by understanding that they're making probabilistic decisions. Because there is only one math for uncertainty, and that's probability theory. Okay, that's the end of the talk. So this is what I call the magic equation. If we look at the history of the last 10 years of speaker and language recognition, this equation in various forms and in various domains has kind of driven what we do. It is a nice, simple equation, but sometimes what we do gets harder. And the general idea is that we have, in terms of speaker recognition, we have an observed vector. We have a true speaker who generated that vector, which is what we want to know. He's been corrupted by speaking in a channel, and that's something we want to get rid of. And there's some kind of an additional additive noise that is making this a latent observation instead of getting to see it directly. That's the general model. Our theme is additive, independent, and Gaussian. That's the one that lets us make all the progress with our mathematics, as you will see as I go on. So that's kind of the magic equation throughout this talk. So what I'm going to do is give a brief overview of GMM subspace methods, which becomes I-vectors, which is our latest hot thing in acoustic speaker and language recognition. Then I'm going to talk about language recognition first, because it's actually a more straightforward task to explain and to understand. And then why speaker recognition is harder and why you have to get a lot more Bayesian, or at least you should consider being more Bayesian to do speaker recognition. And then finally at the end, I believe I will get there. I wanted to give you guys your full hour's worth, so I have actually quite a few slides, but I expect to get all the way to the end and talk about some of our recent work. Especially these will be mainly Daniel's slides on domain adaptation that we did for our Scale 13 speaker workshop, if any of you have heard about that. So GMMs for speaker recognition, just in a very simple nutshell. you start with the idea, or historically, like 20 years ago, the idea was speakers have a pattern of sounds that they use. Acoustic speaker recognition should be that we build a code book for each speaker, how he says things, and then when we have a test cut, we say whose code book does this match, and that's our speaker decision. Now, the thing that Doug Reynolds did, who overlapped with me at Georgia Tech back in this era, and Rick Rose, who was a student of Tom Barnwell's right before me, is to say, let's use a probabilistic formalism for this codebook mapping, which is the way I interpret a Gaussian mixture model. It's you still have this codebook of acoustic sounds, but you have a probabilistic fit for each vector to which sound does it fit into. So the extension here is you have a GMM for each speaker, and your test cut, you're going to say which GMM does that speaker hit against. But the big breakthrough, and I'm going to talk about this quite a bit more, about 10 years ago, was rather than have a GMM for the speaker, let's have for every audio cut a different GMM. And the reason is because in our field, our observation is an entire cut, and it comes from a speaker, but if he's talking on a different phone and we try and match this recording versus another recording, there's that channel distortion, which is just huge in our field. So if we say every GMM was generated by a speaker in a channel, that's what brings us to our modern techniques and gives us this 3 times performance improvement that we've been able to see. And as I'll have a brief touch of the history, basically that started with things like eigenchannels and eigenvoices. It's that sort of mathematics. It then became joint factor analysis, and then it became I-vectors. But it all comes out of that concept.
You don't give any citations for that section?
They're coming.
Yeah.
So the JFA here is the JFA citation. Patrick actually has very many papers, as anyone in our field knows. And actually, this technical report is easier to read than any of the research papers. So here is our magic equation. As I said, we're going to have a GMM for every audio cut. The trick is we're going to make 2 pretty strong assumptions. One is that all of these GMMs differ only in mean. Their weights and their covariances are the same. And the other is that we're told the frame alignment for this cut to the Gaussians in the GMM. Those 2 assumptions allow us to make a very simplified math for this problem. And in particular, it means that we can stack all of these, that the speaker and channel vectors that we're trying to find hidden underneath our signal can be represented as supervectors, we call them, which is a stacking of all the means of all of the Gaussians that are in the GMM. So this is like a 100,000 dimensional supervector that represents the underlying GMM that corresponds to an audio cut. And again, if we make the assumption that that leads to the fact that if we make the assumption that the speaker and channel supervectors are Gaussian, that leads to this solvable mathematics. Jason?
So is the first assumption big?
Well, first thing is the assumptions are very effective because these systems are 3 times better than any of the systems that came before them. In speaker recognition, even if they were actually different in more ways, you don't have enough data to estimate those other parameters, so it's better to constrain the problem space. In language recognition, where you have more training data, it might be interesting to try and relax that assumption.
So I'm probably a little bit confused about exactly what you mean by GMs, and the GMMs differ only in mean. So suppose there's an owl with a very large, that covers a very large portion of the space. Are you saying that you're going to cover that by a lot of different values?
No, a GMM is for a speaker in a cut. Everybody's speaker has a set of sounds. Everybody has that same vowel in some sense. So a Gaussian is a sound by a speaker. Each speaker says that sound a little bit different way. So each speaker has a different mean for that Gaussian.
Thank you. Okay. So you're not saying that the variance or the covariance matrix is going to be the same across different phonemes?
I'm not saying it's the same across Gaussians. It's not the same across Gaussians. It's across speakers.
Got it. Thank you so much.
Yeah, good. That's a big distinction. Okay, now perspective-wise, so it's going to be a recurring theme here. There's kind of different ways of looking at these things. This was developed from a factor analysis perspective. That's not my favorite perspective. I like to think of it as covariance matrices, and the subspace is a PCA decomposition of this. So the key point is we have these underlying supervectors, they're Gaussian, they need to have covariance matrices, which is the speaker and the channel, or the across class and the within class, because speaker is what we're interested in, and again, and channel is what we don't want. They can't be 100,000 dimensional square matrices. That's not interesting. So we want to make a subspace decomposition. In terms of PCA, it just says we're going to do an eigendecomposition of these matrices. In terms of factor analysis, it says that speaker and channel are represented by factors which lie in a subspace, and this U loading matrix is what gets you back to a supervector from this subspace vector. These are mathematically equivalent perspectives. Okay. Is Glenn here today? Too bad. I put in a slide just for Glenn, and he's not here today. So there was a lot of mathematics that got to here. These are some of the hardest papers to read that I think you'll see. And then there was a grad student of Patrick Kenny's named Najim Dahak who came out and said, you know what, I don't really want to do all the statistical stuff. I want to take these factors that you're estimating from the cuts, and I just want to throw it into an SVM. And the reason I put Glenn's name up here is the first time I met Glenn, I guess the first time I came to the COE, we were talking about one of his awesome scales that he did a few years ago. We were talking about we could do language recognition. And he said, oh, you give me some features, I can throw them into an SVM, we'll make a classifier. So that's basically what Najim proposed. And you have to understand, to these fully Bayesian people who don't even believe in discriminative training, this is a really shocking concept. And for the grad students in here, I would just say, if you want to do something that is completely against the philosophies that everything your advisor believes in, it better work really well. And you better be prepared for some somewhat contentious advisor meetings as we hear the stories. But the fact is, it worked, and that's why we're here to talk about I-vectors. So the experiments were, let me learn the speaker and channel factors, let me throw each of those into an SVM. Then you've got your sort of normal experimentalist approach. Let's try them all and see which one gives me the best performance. It was interesting to the community at the time that channel factors were useful for speaker discrimination because people thought that they wouldn't be. But in fact, what worked best was to use both of them at the same time. And if you stack those two factors together, or sort of the math is equivalent to making a bigger factor, which is a single factor instead of joint factors, and we call that total factors. And that is what I-vectors are built off of, as I'll explain in a minute. And the other interesting result is you don't actually need an SVM at all. You can throw them all into an SVM, or you can just take the cosine distance between vectors and call that a score, and you're done. So that was Najim's great success, and I think if I didn't say, that was done at a CLSP workshop in 2008. So some of you might have been here, maybe even participated in that. But that did kind of throw the Bayesians a little bit. I don't know, maybe Daniel can correct me if I'm wrong on this part. But the recovery was, okay, now we'll just call this a two-step process. I-vectors are our features, but we're going to do statistical pattern recognition on the I-vectors, and those are going to be our systems. And as long as we do that, we're still being statistical. So what that meant is they can continue to work with I-vectors, but they can't do cosine distance. And any of us who worked on the scale over the summer, you might remember this as being a recurring theme, an ongoing battle within our scale. Jason.
So I think I'm going to be lost if I don't make you define I-vectors a little bit more than...
I'm about to.
The second bullet. Okay, thank you.
And you are right. You deserve it. Yeah. So in terms of the original notation, then, an I-vector, if you remember, I said before there were two factors, a speaker and a channel, or two supervectors, a speaker and a channel, which are both latent and not observed. Now we're saying there's just one, which includes both. In terms of factor analysis, it's not really joint factors, it's a single factor analysis, and that factor is called an I-vector. In terms of, again, PCA and covariance, it says we have a total covariance, which is sort of the sum of the within class and across class, or the sum of the speaker and the channel, and that total covariance is what we're using to understand what this hidden mean really looked like. The equation, which I'm not going to fully explain for the I-vector estimator, is this one. If you've done eigenvoices or something else, you will recognize it as the same equation in my somewhat unusual notation. It's sort of like a pseudo-inverse kind of a projection. The hard thing about it is that this noise matrix in the middle is actually cut dependent because it depends on the counts and the alignments of the frames. So you can't pre-compute all of these things like you would like to be able to do. Yes?
So earlier, when you had that decomposition, there were a set of parameters associated with the speaker, and
There was a speaker and a channel.
There was a set of parameters with constant C.
Yes.
And the idea was that you need what? Speaker and channel labeled
Right.
data in order to estimate
Right.
all of them. And now, at least for now, you've gotten rid of the speaker altogether.
Right.
These are just
Exactly. So for now, we have lumped those together. We realize, or should realize, that this I vector still contains both a speaker and a channel. And when we go and do our statistical analysis of I vectors, we're going to break it apart again. I think I'm going to skip. How to estimate the T matrix is a bit of an art. There are two perspectives. That's all I want to say about it. Okay. So that is, in an overview, is what an I vector system does. I'm going to go in more detail for language and speaker recognition of exactly how we do this. But I want to sort of stop for a minute and say, what are we going to do with this thing? So if an I vector is a new feature and we're going to build recognizers on this new feature, what should they do? And this is important when you talk about speaker and language. There are acoustic differences as well, but fundamentally the tasks are different. And the tasks, there's a wide range of tasks that you could be doing. So at a high level, you've got identification and detection. Our community tends to focus on detection, but they're kind of equivalent questions. They're just phrased in different ways. And you've also got closed set and open set, which is a big distinction to us. And I guess I'm one of the few people who thinks all four of those possibilities are interesting. What people tend to think of is closed set ID and open set detection. But in fact, closed set detection is a legitimate thing to do, and open set ID is a legitimate thing to do. The mathematical way that we go back and forth between identification and detection, or that we use our raw system scores to do detection, is we compute a likelihood ratio. In our field, again, we're detection focused, and likelihood ratio is the main formula that we want to be able to estimate. So if we've got these likelihoods for all of our classes, likelihood ratio is target versus non-target. And target is the class of interest, what was the likelihood of the data given that class of interest. But non-target is actually a pretty complicated thing. And that's where the equations, the applications come in. But basically, non-target is a combination of it's one of the other guys and it's none of the above. And this out of set prior, out of set being none of the above, is the combination term between those two. So this is Bayes' rule written in a way that you're probably not used to seeing Bayes' rule, but it is in fact just Bayes' rule. So a couple of things. One is the way we do closed set detection is we actually do ID and then turn it into a detection probability, or a likelihood ratio. And the other thing I want to say, which I'll touch on again later, is the nice thing about this formalism is you can have non-flat priors for your classes. You can say an application says, okay, I'm looking for Spanish in a sea of English, as opposed to I'm looking for Spanish in I don't know what. You can represent the fact that you know you're in a sea of English as a different prior. You don't have to retrain your system, because your system is just generating likelihoods for all the classes. It's only Bayes' rule that you have to redo, which is a lot easier than retraining. And one other thing that I'm not going to talk about, there's many things I'm not going to talk about in just this time period, is what we call calibration, which is how we take raw scores and turn them into meaningful units of likelihoods, which is necessary for Bayes' rule, well, desirable for Bayes' rule to work. In our field, the NIST evaluations are extremely important. It's very hard to write papers without having SRE or LRE scores. I'm going to talk, as I said, about language first. LRE over the years has typically been a closed set detection task, which again means the question is it the target language or is it one of the others? There is a significant part of our community that considers that not to be a valid task and essentially refuses to plot debt curves for closed set systems. Nico Broomer is kind of the head of that part of the community. And I guess I would agree that identification might make more sense, but I'm perfectly happy to flip it around and call it detection if somebody wants to. And then SREs, by contrast, again, I'll go into this in more detail, are typically out-of-set detection. So they're not closed set, they're out of set. So let me go into language recognition a little bit more now. So we've got these I vectors. How are we going to recognize languages? Back to our sort of magic equation. This is following up on Sanjeev's statement. We started with supervector versions of these equations, and we had speaker and channel in supervectors, and we were trying to recover them. Now, as I said, we're doing this two-step process. So now what we're going to do is we're going to apply the same similar model, but in the I vectors. We use that first factor analysis to get us to I vectors. Now we need to extract the good stuff from the bad stuff. And I'm still kind of using S because I said speaker and channel, although in this case I'm actually talking about language, but I don't feel like flipping all the symbols every time. So now we have this decomposition that we need to recover. We want to say, did this vector actually come from that language? And it's been corrupted by a channel. And again, with this additive Gaussian model, this is in fact very easy. For language, I'll explain this more, but language is sort of a typical pattern recognition problem that you're familiar with. You have a ton of training vectors from a bunch of different classes, and you learn you learn a model for each class. Our model is, if we have this Gaussian model, we just need a mean vector for each class, and that's all we need for discrimination. So the task is to learn the language means. The channel is assumed to be Gaussian and the same for everybody. That gives us a shared covariance linear Gaussian classifier, which is basically one of the simplest ones that you can do and actually works surprisingly well for language recognition. So again, the training process is we have to learn two things. We have to learn this shared within-class covariance, which is the channel corruption, how it affects all the audio cuts. And for each of the languages, each of the classes, we have to estimate their mean. And scoring is just Gaussian scoring, so we have I just sort of wrote the equation, but the likelihood for each language is just the Gaussian given his mean and the shared covariance, and the detection is done by a likelihood ratio comparing it against all the others that it could have been. So again, in this formula, as I said before, language detection, flat priors is the hardest case, so it's a good one to be able to solve. It's a good one to be able to measure against. But it's not that likely that that's what you will actually see. You would expect that you're in some domain where some languages are going to dominate. And again, with this Bayes rule, it's easy to just adjust the priors. And in fact, one of the kind of nice things you can do, not under the LRE rules, but in a real application, is you can use your system to estimate what languages you think you're in, and then you can plug that back into your system as priors, and you can actually make it work better. So you can adapt to the language environment that you're running in and get a big performance improvement. One other thing that I'll just touch on is this is a very simple model. One way you can help it is doing discriminative training. Of course, that's a standard thing with a generative model like this. This is actually kind of a bizarrely easy case of discriminative training because these kinds of algorithms, I guess Dan Povey is not here. He seems to always sit over there when he's here, so he's not here. Dan's thesis, if you guys didn't know, was on MMI and MPE for discriminative training of HMMs, which is, this is just one single Gaussian and nothing else. So it's the same algorithms, the same mathematics, but it's actually much simpler. And ironically, some of the algorithms don't behave, and some of the algorithms, in particular the one that Dan focused on, doesn't actually work very well in this context, where it did in the other, in his context. An important point to make is most people think of discriminative training as improving the decisions, and that's certainly what we're interested in doing as well. But we are also interested in calibration, and we can accomplish both in this very simple model with that discriminative training. Whereas in speech recognition, they really don't even try to do that. They have something else. Okay. So language recognition in iVectors is really pretty easy. It's just Gaussian classifiers. Why is speaker different, and why is speaker harder? So, and why did people go all Bayesian with speaker? So basically, again, in language recognition, it's a typical multi-class ID task that you're probably familiar with. You've got a ton of classes, or a reasonable set of classes. You've got hopefully quite a bit of data for each class. You can learn what they look like. Speaker has two funny things. One is there's only one class, and the second is there's only one vector to learn what the class looks like. That's the way an SRE is typically run. And if you've never looked at a task like that, you should realize that's pretty odd. So the question is this test cut from the same speaker as that enrollment cut was? That is the SRE question. And that's why it has these characteristics. So in terms of the math that I was talking about before, there's really, I would split out, there's two problems that this introduces. One is you don't get to know any of the other classes. So you're going to have to make a non-target hypothesis, but nobody's told you what it should be. The other is the speaker model that you are interested in learning about or scoring in the numerator, you only got one cut to learn what it looked like. And that's kind of hard. So I'll break those into two parts. I'll talk about the out-of-set problem first, the fact that you don't know the competing speakers. And I'll come back again to this magic equation. And again, we don't know the actual, we're not allowed to know anything about the imposter speakers who are actually in a NIST SRE. So what are we going to do? We're going to take all the other speakers we could ever find from any past NIST data and learn what speakers look like. And we're also going to learn how channels corrupt speakers by looking at all the other speakers that we've ever seen and seeing how they got corrupted. That allows us to build a non-target hypothesis with this probabilistic model, as the non-target is it's a random speaker in a random channel. And because everything is Gaussian, that's just, it has the average mean and it has the sum of the two covariances. So that gives us a non-target hypothesis to sort of get around the out-of-set problem. Now, the learning a model from only one cut is where we have to get Bayesian. Yes, Jason?
Just a practical question. If you're making an engineering decision for to win all those speakers equally, all the other speakers that you can find, whether that's a good assumption depends on the what you expect your test data to look like, you're discriminating between members of the same family or
yes,
whatever.
absolutely.
But in practice, do you weight those speakers by type or by token? In other words, if you have twice as much data from Sanjeev as from me, then you just throw it all in and you're not discriminating.
Right. There's actually two parts to that question. I would say the first part of that question is, yeah, is it everybody else? We tailor it in a NIST SRE to what we think NIST is going to use as the competing speakers in the actual evaluation. And in the NIST evaluation, they use only same gender speakers, so we therefore build separate non-target models for each gender. Not necessarily that we would really do that, but the NIST structure, we're trying to guess what, the way to get the best answer in their evaluation is to guess what they're going to do. And they actually tell us that part, so we should take advantage of it. Now, your second question is, should we weight them evenly or not? That's actually still an ongoing debate that Daniel and I have, and it kind of depends on the circumstances.
I should repeat something that may help Jason's thinking about it. It took me a while to realize this, but the way I think about it is, normally when people say classification problems, you have pairs x, y given to you, x is your observation, y is your class value, and let's say y takes values 1 through 10, and in your test data you'll be given an x, and you have to decide which of those 10 y
Right.
it is.
Right.
Here's the setup is, you're given lots of x and y as training data, and the y take values 1 through 10. And at test time, you'll be given two x's. They're either both from class 11 or they're from class 11 and 12. And you have to decide which of those two is.
Yes.
So it's not your standard classification problem. The classes you had in your training have nothing to do with the classes in the test data. They're two samples, and you have to decide whether they're from class 11 or class 12. Neither of
Right.
those will be any class, whether they're from the same class or whatever.
Yeah.
And my question is, in the distribution over classes, are you more likely to get samples from people who talk more? The question again, how, what your test data looks like.
Yeah, there are the logical questions, and also, maybe some speakers are either more similar to the ones you expect or in environments that are more similar to the ones that you would expect, so how do you weight that? Absolutely, that's a fair question. And there's no magic answer. Yes, Scott?
So is your system output same different, or does it follow?
Our system output is a likelihood ratio, which is same and different, yes.
Okay, on these two cuts that were conceivable.
Right.
Yeah. I'm just trying to understand.
Yeah. Right. Okay, so that's the good. It's important to understand that distinction with speaker, because otherwise what we're talking about, you don't see why it's so hard. Okay, then the other question, again, is this Bayesian question. We only got one enrollment cut, how do we learn a class from one instance of a training vector? And so here, that's where you start to get Bayesian. Of course, what I talked about in language is you just do ML, you take a sample mean. The next thing most of us would do is do a map adaptation, which I think is sort of more Bayesian. What I call fully Bayesian is to estimate the posterior distribution of this mean given the training data and use that distribution rather than a point estimate when you do the scoring at test time, which is using a predictive distribution. As you'll see, we have different perspectives. So fully Bayesian to Daniel means that you estimate the posterior distribution of these covariance matrices themselves and use that as well. So I'm going to start. I'm actually going to present 3 perspectives for this kind of modeling. I'm going to start with the one I like best and then move to the others. I call it Bayesian speaker comparison. This is a pretty simple math that is, in fact, pretty well known, but it's not the way we usually think of our problem in our field. So the problem statement is we've got a set of I vectors, which might be 1, which is the training data for a particular speaker, and we have a test cut, and we're trying to make a likelihood ratio.
That's what you call enrollment in the earlier.
Yes. Yes.
So it could be up to n enrollment.
Right. And the way I would like to do this is a likelihood ratio is XT, did he come from, is he from the same speaker that generated D, or is he a random speaker in a random channel, which is what I call that denominator. So the interesting question here then is the numerator, and the Bayesian way to do that is to integrate over all possible models given the training data D, and that's done in this way. So hopefully you guys have seen that kind of stuff. And this is why, of course, we like Gaussians, because anybody who's done Bayesian stuff knows that it gets really hard unless you have really simple models. And basically, this is probably the only problem that has a simple solution in all of the Bayesian world. So why don't we start with that one? And then this posterior distribution of this mean is, the mean itself is what you see when you do map adaptation, but now you're keeping an associated uncertainty covariance, and these are my mean and covariance that came from the data D. And this covariance will shrink to 0 if you have tons of training data, but if you don't have much training data, it's the Bayesian representation of your uncertainty because you didn't have enough data. And then at test time, you can take the likelihood ratio between this sort of, and again, this integral of Gaussians just gives you a sum of covariances, sum of Gaussian. That's the beautiful thing. It just gives you a fatter Gaussian. And again, this numerator would look, this numerator would look like what we did for language recognition if sigma d is 0, which is to say, if we know everything about our training data and we've learned our class successfully, then this Bayesian component will disappear. But if we don't have enough training data, and in SREs we definitely don't, this term contributes quite a bit to our answer. So this is the one perspective. Another perspective, which is maybe less well known but certainly very important than PLDA, which I'm going to come to later, is the Two Covariance Model. It is, the hypothesis test is the same likelihood ratio in the end, but it's broken apart in a different way. The numerator is, are these the same, and the denominator is, are they different? So this was sort of Scott's way of presenting it. This likelihood and that likelihood are not the same as any of the things I had in the other formalism, but the ratio is the same. And the math for this, again with these Gaussians, is you stack x1 and x2 and make a bigger vector, and you evaluate it as a big Gaussian with a covariance which has 4 components which all depend on sigma c and sigma s in pretty simple ways. I'm not deriving the whole thing, but the fact is it's fairly simple to set this up as a stacked vector, evaluate this likelihood, evaluate that likelihood, and take a ratio. It gives you, again, the same answer as the other approach, but it's not the same question. It's not the same way of getting there. Another thing about our field, so Nico Broomer kind of gets, well, as far as I know, developed this. This farewell to SVM, again, tells you kind of some of the theme of how our field works. Because at that time, people were doing SVMs in supervector space, and Nico was trying to come back to statistical models. So to compare these two formalisms then, this is the speaker comparison one, and this is the two covariance. In this situation, we have speaker models, but they're uncertain, so we represent them with posterior distributions. And then the hyperparameters of this system are the covariance matrices sigma c and sigma s, which define the Bayesian, which are the priors for the Bayesian problem. In the two covariance model, and in their mindset, there is no such thing as a speaker model. There's only a same and a different. And the parameters of this system are the covariance matrices. And this is why the difference in formalism of the Bayesian stuff from before. Okay, now, yes?
So on the right side, does this mean that, whether it means that I can live without having a lot of other speaker-labeled data in principle, or do I still need that in some?
These are two formulas that give you the same answer using the same hyperparameters. It's only a perspective.
And the addition of the speakers on which I estimate them, those are separate from the actual task that
yeah, it's all of these are still using, right, the sigma S and the sigma C came from another pile of data.
Okay. So those are still there on the right. I mean,
yes.
Left, they're very explicit. But
those are the two covariances from the name. That's what they are. So the term that you'll hear is PLDA. That's a third method, which I think maybe Daniel and I would agree is really just a dimension reduction on top of the two covariance model. It's a formalism that came from actually from face recognition, which has some similarity to this same different sort of mindset in face. They have that also. But what we're doing here, so hang on. So we have, these are our two models, but the fact is dimension reduction can still be helpful. It may seem kind of funny because we already did this massive dimension reduction from 100,000 to 600, but in fact going down to 200 can be better still. The way I would do that, since I already have these covariance matrices, is do LDA, and the principal directions are quite easy to find, the most useful directions. But this other formalism, which again came more from a supervector kind of a world, is that you can jointly estimate sigma C and sigma S where sigma S is reduced rank in this EM algorithm that's called PLDA. So in practice, this is using the same kind of scoring formulas as we did in two covariance model, but we've got dimension reduction built into it at the same time as you're estimating the matrices rather than afterwards. So to kind of summarize how people build speaker recognition system, there are three different things. We maybe for convenience might call all of these PLDA because that's everybody's favorite buzzword, but Daniel's the only guy who actually does it that way. What I'm going to do is take the covariance matrices either by sample matrices or by a joint EM, and then I'm going to do LDA, and then I'm going to do my Bayesian comparison. Daniel does PLDA for everything with one algorithm. What some of the other leaders in the field, the Bruneau guys and SRI, will call PLDA is they actually do LDA with sample covariances, and then they do what they call full-rank PLDA, which is almost an oxymoron, which is the two covariance model applied to this already dimension-reduced space. But the dimension reduction happened from sample covariances, and then you estimate the covariances again with an EM after that. So, yeah, so what people call PLDA is actually kind of confusing. So, my opinions, and Daniel got me to put a footnote in, I don't think the PLDA terminology, especially applied in I-vectors, is actually that good a way to look at it. Why it's good to me is because it gives the right answer. One thing about this stacking of vectors on top of each other is if you have more and more cuts, you just stack higher and higher and higher, and that's not a very good way to generalize to having more training data. There's really no relation. In this BSC formalism, we can say an ML model was just a special case where that uncertainty went to 0. In this kind of terminology where you had no models, you've got no analogy to the known model case. It's just, you've just pretended it's a completely different problem. And then finally, this sophisticated dimension reduction isn't really very interesting when you're already in the I-vector space, and LDA works just as well anyway. It's not doing EM, but it's using kind of a better discriminative criterion. So, yeah, that's my opinion. But the one thing we agree on here is gee, we could actually do this right. So we had this two-step process where we did I vectors on the one hand with one set of mathematics, and then we said, okay, now that we're given I vectors, let's do something again, which is Gaussian, speaker, and channel. And they were very similar models, but they're not the same, and they weren't self-consistent as a coupling. So can't we go back to the original supervectors and set up this problem right and do it in one step? And the answer is we can. It's a lot like JFA, but if you look back with the benefit of hindsight and the realization that actually, the first time I met Daniel was we were sitting in the back of the room in some JFA talk or other, and he said, you know what, these two spaces, they're not different. I've gone and measured these subspaces, and they overlap a ton. Everybody in PLDA thought that these two must be completely different spaces, and that was the beauty of the process. The math never said that. The math just said they're independent variables, but they could be independent variables that lie in the same space. And anyway, the key to doing this right now is to say, no, they are actually exactly in the same space. Then let's derive the answers. And you end up being able to completely solve in a Bayesian way, which the JFA people had to make all kind of approximations because it became too hard. We can do it right. It is like a PLDA in supervectors, or you can do it in both ways. So I think there's a nice theoretical beauty to doing it all at once. The practical value isn't tremendous because it does work better for short duration cuts because it's modeling all of the uncertainties in the GMM. But it's also more complicated, so you might not be willing to go through the penalties of doing it. But, gee, isn't it nice that you could actually derive that whole thing?
For long durations, it's the same.
I'm sorry?
For long durations, it basically gets the same.
Yes.
Not worse.
Yes. No, you can actually show that it is, I vectors is the long duration approximation to that correct solution, and it's a perfectly good long duration approximation. Okay, so I'm going to try and go to some new work at the end, but so what we got so far is basically an I vector is a low-dimensional estimate of a GMM. Again, this key concept is we have a different GMM for every audio cut. That's kind of an unusual concept, but it was very important to us. It includes both speaker and channel, therefore we have to do something about channel now that we're in the I vector space. For LRE, you can just do this really simple Gaussian modeling. For SRE, you got to do something Bayesian if you want to get state-of-the-art performance, and there's a bunch of different ways to look at it. Okay, so to give you your money's worth, I'm going to go through a couple of our recent results. With that sort of setting the stage, these are on speaker recognition, and I want to thank Scott for a good talk last week on domain adaptation in a little bit of a different context. I guess almost every field has at least thought about this question. And we were quite excited. We were able to make a lot of progress this summer, I would say more than we expected, so it's kind of nice. So the problem statement, again, is we have a speaker recognition system. We have a test environment that we don't get to look at. We have some pile of data that we build our system off of that we think looks like what the test data is going to be. Normally, we would just have one pile, but we know in this case that that pile is out of domain and it's not going to match it all that well. So we want to have an in-domain pile as well, and we want to combine both piles to make a better decision. Doug Reynolds from Lincoln Laboratory was kind enough to build a very nice set which demonstrated this problem. Basically, I won't go into details of what they are, but our in-domain system is Mixer. It's more recent LDC corpus. Our out-of-domain system is an older LDC corpus called Switchboard. And in fact, just learning our PLDA hyperparameters off of this out-of-domain set gave us a much worse performance. So that this gave us a really good problem to work on because we had a big mismatch. And actually, another thing I'll say here is with this terminology, Daniel and I have reached a kind of unwieldy compromise that we say we're doing PLDA with in-class and across-class covariance matrices as hyperparameters, which is not really correct in anybody's formalism, but we kind of all know what it means. Okay, so this is a plot of supervised adaptation, which is what if somebody labels for you at least a small amount of that pile, how can you use that in-domain pile to do better? And the red and the green is what we would have gotten, what we get with an in-domain system. The red is the out-of-domain system. There's a big gap. With 100 speakers of labeled data, we're able to close 70% of the gap, which is pretty impressive. And of course, it gets better. And if you use all of our data, which is almost 4,000 speakers, obviously you end up with a full system. So that was interesting. There is a math behind this. I guess that Daniel was kind enough to use the covariance matrix formalism for this slide. So if you're trying to estimate a Gaussian covariance matrix, a prior is an inverse Wishart if you know the means, and you can rewrite it in such a way that it looks really simple, which is very useful for us in this application, which becomes just essentially a linear smoothing between the out-of-domain estimate and the in-domain estimate. And you can do that for both speaker and channel. One thing I promised Scott last week is, because he has an analogous thing to this alpha, is we have a nice plot of how it matters. So again, this is labeled data. If you've only got 100 labeled speakers here, and if you've got many labeled speakers, it goes this way. If you've got only 100 labeled speakers, you can see that the out-of-domain system always is over here. You have a very deep bowl, relatively speaking, between a pure in-domain system actually sucks because it doesn't have enough data to learn its parameters. But with this, there's a fairly decent bowl here of alpha in the middle where you get much better performance than either side. As you have very much training data, of course, it's essentially all the way at the bottom at the left. But still, you can get there's a slight bowl, and of course, mainly you're getting a big drop, a big improvement by going in-domain from the out-of-domain system. But I think our main takeaway is it's not like alpha has to be 0.63 or it's not going to work. It's really not that sensitive to what the alpha is. Okay, the last thing I'm going to do is unsupervised domain adaptation. This was, so Daniel and I have had a number of little side bets as we've been working together. And this is one that I can say that I won, because as we set up this task, I said, from looking at some other people with kind of similar systems, that I thought this would do something. And Daniel said, why would this be able to do anything? If all you've got is an unlabeled pile that you label with your own system, how are you going to learn anything that your system didn't already know? And I agree with him philosophically. So the problem statement here is, again, we have this in-domain pile, but now nobody's told us those labels. We have to figure them out for ourselves. The recipe is that we basically use our out-of-domain system to compute a similarity matrix. We use that for a clustering algorithm to generate our labels, and then we adapt our algorithm using that labeled data, self-labeled data. And while I agree with Daniel philosophically that probably shouldn't work, we get 85% of the gain back that we lost from a mismatched system just by self-labeling our pile without any labeling at all, which I think we should step back and be impressed with, even if we don't really understand how it's possible. Okay, so that was a very quick summary to a lot of pretty interesting work that we'd be happy to talk to you guys about more at some other time. The main point is that domain mismatch is a big deal for us. Even within sort of SRE style of data, we were able to see big performance drops from mismatched domains, which was kind of a surprise. And I think we can easily imagine much bigger domain mismatches than that. Supervised adaptation works really well. That's probably not so much of a shock. But the numbers we were presenting were 100 labeled speakers. That's a fair bit. Even our smallest set was a fairly big amount of labeling. I think the big surprise was unsupervised adaptation actually works better than that if we have a bigger pile. And it's not hard to get a bigger pile of unlabeled data. It's the labeling that's the hard thing to get, right? Okay. So that ends the whole talk. We kind of had two parts here. One was, what is an I-vector system? I think I didn't emphasize too much, but it's one of the reasons it's so attractive is it's really simple. Once you've extracted these I-vectors, you've got really low-dimensional vectors for every cut, and classification is a pretty simple process. Everything was based on this additive independent Gaussian assumption at various phases within the process and various permutations of the algorithms, and there's multiple ways to look at it. And then I think I touched on some of the things that we're interested in, which is basically everything to do with speaker and language. We're interested in theory and in improving the performance. We're interested in the LREs and the SREs and trying to get the best possible numbers. And we're also interested in this, what would you have to do to make it useful in a real situation. And eventually we're going to move beyond I-vectors, I think. We're starting to talk about deep neural networks. Who knows? Okay, so that concludes my talk. Thank you very much. Any questions?
I'm always good for a question.
Yeah.
I've got a couple actually. Just picking up on your last comment about deep neural networks, is that because you don't actually believe in the Gaussians?
It's because even Daniel is a pragmatic Bayesian person, so
Yeah, it's
we're
pragmatic
willing
enough
to
to use the
explore
Gaussians.
other things that work better.
Using Gaussians is pragmatic because it's obviously the wrong model. So, if you're a real Bayesian, you have to use the right model, otherwise none of it makes any sense. And that's why we wrap curriculum methods around these things and do calibration. So, is the reason that you want to go to deep neural nets that you don't believe in Gaussians?
I mean, it's not that we don't believe in Gaussian, it's that we want to look at longer context. That's the main reason why.
In other words,
But you don't believe the independence assumptions of using the Gaussians.
I didn't
We
talk
never
about.
believe the frame independence, but we don't
Yeah.
have the ability to look at longer chunks of data, or we can extract.
Yeah, I didn't talk much about feature stuff, but especially for speaker, we're using one acoustic frame, MFCCs, and a couple of deltas.
Right.
And one of the things we find attractive is to be able to use 20, 30 frames in a row and look at how things are evolving. And in a GMM, that's very hard to do because it becomes such a complicated vector you can't model it, and that's what the deep neural net guys do.
Good. Thanks.
I can ask one, so when I think about recognizing speakers, like I would probably also look at things like the speed of speaking. I would get Jason right there, or I would look at shifts in a phoneme space. I would get Hinek right there, and stuff like this. I mean, as many all particular words, I would get Hinek again. I mean, because somebody likes using certain words or accents. When it comes to languages, I would definitely think about the words, which are being used, or at least the engrams, or stuff like this. Is it all gone, all these approaches? Because, we were used to think about it, but it seems like that any time somebody comes with some powerful statistical techniques, people essentially start asking for more data, adaptation data, and at the end they win. So how?
No, not
what is your opinion?
So we call, somewhat sloppily, we call those high-level systems. For example, things like "What did people say?"
Mm-hmm.
And I think sorry, I didn't have time to touch on that here. In language recognition, n-gram-based phonotactic systems are directly competitive with I-vector systems as the two best kinds of things, and they will fuse to give you a better answer. In speaker recognition, people have always been looking at this. As you know, there was quite a lot of effort. It is not currently competitive with the state of the art in speaker, but people are continuing to look at it. And one way we kind of hide that is by taking bigger features that look at other things, even if we put them into these kind of acoustic models.
So you think that if the paradigm changes somehow, you also strike me like that you guys are under the thumb of NIST, whatever NIST decides you do, right? But, is that the right approach?
We have a little bit of
because we,
freedom.
of course, can say the same thing, whatever DARPA says we'll do. But I kind of feel that maybe this is not the most honest approach to when it comes to science or something. And so, of course, you mentioned that you cannot write a paper unless you put in the NIST results, which, of course, has something to do with the field and the reviews and that sort of things. I don't think it's correct. I think it's wrong. But we might as well accept it. But do you think it's good or not?
Well, I think the trade-off is clear. I think evaluations are good because without a common framework, you can't tell what works. But only publishing papers that win evaluations would not allow progress, certainly. So
it's like my friend.
Yeah, I think Jack may have an opinion.
Yeah, my friend Jordi says that, Jordi Cohen, he kind of says that you should judge things by the beauty of the approach.
Yeah,
I wonder
we have some belief
that is still a little bit actually there, like sort of. I agree with you that people are so uncertain about what they are doing, that the only way to show that you are making the progress is that you show the better result. Because people don't look much into what you do. They look at it if it works better.
I disagree. I think that we appreciate beauty.
Yeah, but maybe I don't know if you are the reviewer, right? Or whatever,
Well, I'm not the only reviewer, certainly.
Yeah, so I just wanted to bring it up. I mean, since you mentioned it a couple of times, I mean,
We are authors in beautiful papers that not only talk about ideas.
Jack perhaps has a comment on that.
Yes, so try to imagine telling the sponsor that's paying for the NIST evaluations that next time you will present, that you will encourage the most beautiful results instead of the results that do best for the application.
Beauty is just a regularizer here.
So the NIST evaluations are, they may be narrow and focused on an area of applications that's not of interest or not beautiful or scientific. I agree with all of that. But, and let me also drop another footnote in. In 2002, when we got a whole series of exciting results from areas that are not narrowly focused on single acoustic cuts, which is really where the application behind this seems to be.
Jack doesn't want acoustics either.
No, I see the beauty of all those things, and if it were up to me, I would give as much money for that as for the what we'll call them the acoustic single cut base, whatever the results. But consider this number. In 2002, when the so-called higher level features were first studied, they caused a lot of excitement. And one of the reasons that they were exciting is because when you fuse the results of an acoustic system like this with the results of a higher level feature-based system, you were fusing a 3 or 4% error system with a 10 or 15% error system, and you actually got a change, a noticeable change in the result. Now, under some ways of setting this up, you would be fusing a 0.5% acoustic system with an elaborate knowledge-based system that can do as well as, let's say, 5 or 10% error rate. And the result will, for the cost that you have to invest, the net result on a practical application will not be that great. So that has nothing to do with science, and I agree with you that there are many scientific questions to be answered.
I think the real hindrance was right when that stuff was really becoming interesting, this stuff started to kick in, and suddenly this bar went way down.
Right. I think Jason's earlier question seemed to imply an assumption that the Gaussians actually represent in some principled way, the sounds that are being articulated. But I don't think that's true.
Yeah, I wasn't assuming that. I was suggesting that maybe that would be a reason to go to get on that system.
Right.
I mean, all
the difference between this approach and an approach that might know what's being said, and then use that to frame who's saying it.
Absolutely.
The Gaussians that are being used in this system you can view as just a kernel density estimate. They're not actually modeling anything real, right? They're just an arbitrary distribution with which to model a sort of distribution of content overall, right? So I don't think it's meant to be meaningful.
Sure, and it certainly is not capturing. I mean, not only is it not capturing correlations over the span of a second, which is what Daniel's talking about, it's also not capturing correlations over the scale of a language model, which is what Enoch's talking about.
We can, by the way, make I-vectors out of n-gram counts.
Alan, say you wanted to go over this is there anything that's what we in terms of application-wise, there's an engineering task of these sort of short acoustic models are much faster to compute. But if you want to run speech recognition, you incur a large.
Well, one of the problems with the way the SREs evolved is this single cut thing, which is not always the way it was. A single enrollment cut is harder for n-gram based systems because they don't get to see it as n-grams.
I have more of a comment than a question. I was sort of, when this result first came out, that if you want to model a whole speech file as some additive mixture of some speaker effects and some channel effects, and you decompose it into speaker subspace, channel subspace, they both turned out to be about the same, because I was hoping that, how changing a speaker changes the speech is different from how changing the channel changes the speech. But is it because there wasn't just enough data, or is there something more fundamentally wrong with that? Because I would imagine that you'd need lots and lots of speech from one speaker in many channels and so on and so forth in order to really see that separation. In other words, should we give up on that idea, or it's never going to happen?
I'm not sure. I mean,
Or in fact,
we're absolutely
Give up on
using
that.
the covariance, the variations within class and across class are different, and we use that fundamentally as part of our modeling.
No, but why didn't the two spaces come out different when you were estimating them, or when people were estimating
Oh,
them?
there's nothing about JFA that says the spaces should be non-overlapping. It's not. I think it's actually uninteresting. We can talk about it longer, but if the channel space was disjoint from the speaker space, then if you had enough frame observations, you would have a perfect likelihood. And that can't be a realistic model. Because we know that no matter how many frames you see, if he's talking in a different channel than he enrolled in, he's never going to look the same. And the only way to get that behavior out of the map is to have the channel space span the speaker space.
Yeah, I'll follow with you.
It's actually a stupid model to be disjoint.
One thing, Alan, you didn't mention that you might advertise to the whole group is this I-vector challenge idea.
Yeah,
Or if you don't like PLDA, you can replace it.
Yeah, so I didn't make a slide. We are getting together a sort of machine learning challenge problem where we're going to generate a bunch of I-vectors for an SRE-like task, or for this domain adaptation-like task, actually, and put out I-vectors for the world to play with. And if you want to compete and build a pattern recognizer that is better than PLDA, you will be free to do so.
When is the ETA on that?
I think it's probably past, but we're getting close.
Soon,
Soon, very soon, let me say that, very soon.
President Obama and his
Well, the NIST guys are back, right?
Oh, they're back.
The NIST guys being gone hurt that.
Right, so. All right. There are no more questions. Let's thank Alan again.